Okay, so let's continue the lecture of Schotty, the proof of Schotty theorem today. So, okay, so remember that Schotty okay. Okay, so okay, so okay, so last time we showed that. So remember we have this log, right? So we have this like like a scattered log, and then we show that for any okay. So let's recall. So last time we showed that for any let's see any v is c. We show that this real part of the z is within one half of one of the numbers plus minus natural log of square root of n plus 1 plus square root of n. Okay. So basically the idea is that this m kind of scattered along the it's like this is like scattered around, and the difference between the adjacent points, they are less than 1. Yeah. Yeah, it's less than 1. Okay, I think it's actually, last time it was my tempo again. So I read out the wrong way. Remember this anyway, yeah. Okay, and then we say okay, and then we know that the imaginary part of this v is within square root of 3 over 2 of one of the numbers. N pi over 2. Okay. So where is m is the natural number including 0, I think, and then it's 0, because otherwise Otherwise, I don't think it will hold, right? So if it is not, yeah. I think the zero is included. Okay. I forgot to check whether the number includes zero, but yeah, I think this time this part is. I think this zero is being included here. Okay. So yeah, correct me if I just yeah. Yeah, I think it's yeah. This zero must be included. Yeah, this zero must be included. Okay. And then we have this yeah. Okay. And then yeah. If n is in Z, right? Okay. So we show that. Yeah, we show that the sequence of this way. Yeah, so we see yeah, we show that this when the image part is in 0 or 2. I think we showed last time, right? So this so you have like m plus, you have this wherever last time we have this n plus 1 pi I over 2 minus n pi I, yeah, over 2. And then whenever you take the modulus, so which is just what? Pi I, right? Pi I over 2. So the modulus, yeah, modulus becomes pi over 2, right? And this number we know that is less than, yeah, less than square root of 3. Okay, we showed last time. So then if you take any imaginary part, okay, and then basically okay, so because the difference is less than square root of 3, so yeah, it's consecutively like goes to infinity, right? Negative infinity. So any point must be included there. Okay, anyway, so that's so yeah. Okay, this shows what? This shows that so this shows that any disk in the complex plane C. Oh, okay. Having the radius square root of 1/2 square plus square root of 3 over 2 square equal to 1. Let's see. Okay. Must must where is that? Okay, must contain a point that is not in the range of F. Okay, so why is it true? Okay, yes. So because any disk with radius 1, right? So because okay, so why is true? Okay, because the distance between this yeah. So remember that you have this the missing point, right? So wait, shoot. Okay, so you have the point as so the missing point is being defined as this it's like the real part is like plus or minus log, right? So this is like the real part, and the imaginary part is the imaginary part is exactly the other one, which is this m pi I think. Yeah. So the imaginary part is like exactly this m pi I, and then so remember that here this real part is like going that way, and then the imaginary part is like going in the other way. So basically, and then if you pick, and then the distance between the real part is less than 1/2. So it's like, imagine like the distance between these 2 points is less than 1/2. And then this is like the imaginary part. It's like, so here is like maybe something times like n1 pi over 2 or something. And then this is like natural log of the square root of m1 plus 1 plus square root of m1, right? So okay, so here we will increase. So it's like this like lattice plot, right? Where you know that this distance is less than 1/2, and then this distance is less than this distance is less than 1, and then you know that this guy is the distance of this one is less than square root of 3 over 2. Yeah. So basically here we know that this guy is by the triangle inequality, right? So the distance of these two is less than 1, right? Hang on. Oh, okay. So I think having the radius 1. Okay, so having the radius 1. Okay, so if you pick a point, okay, so you know that oh, I see, okay. So you have a point, you know that there's a distance, okay, after a distance of, so remember you are climbing, right? So you start with a point, like any point on the convex plane, And then after you move something, move within yeah. So yeah, you after you move a distance within 1/2, right? And then you get to somewhere. And then after you move again, right? So you move like up and down. And then you move like a square root of 3/2. You get to another like imaginary number. So then yeah. So basically yeah. So basically when they cross, it must give you like the point 1, right? And then you take the distance is less than 1. Yeah. So yeah. So basically that's including I think the reason why he's saying is the proof. Okay. Yeah. Okay. Anyway, so let me just continue. So. Okay, so now, so suppose this theta is in d such as 0 of radius and theta r, where this 0 less than theta less than 1. Okay, and where this theta is phi prime of theta is not equal to 0. Okay. So yeah, and then consider the function fg is equal to phi of theta plus 1 minus theta rz. Yeah. Where yeah, rz. Okay. Over 1 minus theta r psi prime theta. Okay. So okay, so suppose you have a function like that. Okay. So so now, yeah, so because everything this theta is between 0 and 1, right? So yeah. And this r is the radius, right? It's the radius where this function yeah. So this r is like a radius that this function is being defined, and then this phi prime theta is not equal to 0. So we know that this fg wait, what about okay. Yeah, so we know that this fg is being defined on the disk of radius r, right? Wait, no. Oh, okay, yeah. So okay. Okay, so this is a little bit tricky here. So here, what's it doing here? So I think here, because this theta is so theta is a coefficient, right? So theta is a coefficient. So we know that okay, so yeah, so basically you can think of this zeta as being defined on some ratio, like yeah, so you can think of this theta as being defined on over somewhere. Okay, so this is the big R, and then you have the zeta, and then this is like the theta R, right? And then this is like 1 minus theta times R, right? And then, yeah, so here we have, wait. Yeah, so this data is within, okay, so this data is within this disk. It's within this region, theta r. So this is like the center. And then this is like the whole radius, okay. So I will draw it in a full circle, but yeah, this is the, yeah, but this is like the, maybe yeah, but, yeah, so like that, okay. So I didn't draw it very nice. Yeah, you can see that, right? You can see that. Okay, so anyway, so, and then, yes, for any z in the unit disk, yeah, it is true, okay. Alright, so anyway, so let's continue. So, and then what happened is that the function at z is well defined. In the unit disk, and it satisfies, wait, what? Okay. It satisfies the condition of block theorem. Okay, let's see. Wait, why is have why is that? It's defined. To take any z within, oh, okay. Which is what within any z. For the theta r z is what? Using any z equal to 1, then okay, okay. So basically you are multiplying z by, okay, you are multiplying z by these factors, right? What does this factor mean? So this factor means that 1 minus theta, okay, which is that, oh, I see, okay, okay, okay. And then what is the, oh. Theta is a vector, oh, okay, okay. So length of theta is actually less than theta r, right? And then, we know that the length of z is less than, wait, if the length of z is less than 1, then, okay, so then you rescale it to a factor, right? And then the factor rescaling would be also less than, wait, after you scale it, okay, okay, it will be at most 1 minus, okay, yeah. It will be strict, wait, yeah, because the length of z is less than 1, right? So after we scale it, the whole thing has, the whole thing radius is less than whatever 1 minus theta r, 1 minus theta times r. And then, okay. And then this theta is distance less than, okay, okay. Okay, yeah, so it's defined in the unit disk, and then it satisfies the condition of block theorem. y satisfies the condition of block zero. So okay, theta, I know that. Oh, okay, okay. Wait. Okay, we know this theta r is. Oh. Oh, okay. Okay, okay, I see, I see. Okay. Okay. Okay, never mind. Sorry. Alright, so I satisfy the condition of okay. Y is satisfy the condition of block theorem. So okay, let's what is the condition? Okay, so oh okay. Who is single? What is the oh okay, so for the block theorem basically I think you have a sorry. So for block theorem, you have a R, you have a rho, right? And remember that this R wait. So okay, so remember for block theorem, what is the block? Oh, wait, what is the? Oh, okay. What is it? Oh, block theorem. What is it? Let's see. So for the block theorem, what you have is you would have what? I don't know. You have I totally forgot what is block theorem. So shoot, what is that? Oh, okay. for block theorem, we know that the function is being defined over the closed. Okay, initially it was assumed. Wait. Yeah, initially it was assumed in the closed. Wait, hang on. So okay. Wait. Okay. Okay. So what is what is block theorem? So block theorem we have this okay. Oh, I see. Okay. So for the block theorem, you said this f is analytic in the unit, in the unit disk, and then satisfy f prime 0 equal to 1. Okay. Okay. So yeah. So yeah. So yeah. Sorry. So yeah. Okay. Okay. So we know that this fz is well defined in the unit disk, and then it satisfies the and then we know that this f prime z okay, we know that this f prime z is what? If you f prime z, if you take the derivative. Oh, okay. Okay, so if you take f prime, it will be like the chain rule, right? So you use the chain rule, and then yeah, and then you will get this yeah, I think sorry, I just okay. Yeah. So okay, so you take the derivative, you get 1 minus theta r e of theta plus 1 minus theta r z over 1 minus theta r outside prime phi. Okay. Okay, so now what do we do? So what happened? So okay. Okay, f prime 0. This is gone. And then this is gone. And then, oops, times, sorry. Okay. I messed up the chain rule. Okay, sorry. Wait. Oh. Okay. Okay. It's what? Okay. All right. So, all right. So yeah. So yeah, we know that it satisfies the condition of Block-theorem. Okay. All right. So what's next? So let's see. Okay. So now, okay, I see. Okay. All right. So now, okay, what happened? What happened? So so now, because the, the image of the disk D0R under the mapping phi v oh, okay. Wait. Okay. Cannot contain a disk wait, okay. Yeah. Yeah, we put it here, okay. Wait, okay. Okay. Wait. Okay. And then what happened? So wait, why it cannot contain? Okay, let's see why not continuous disk of radius 1. So the thing is that so imagine that party is you okay, so say you have a disk of radius 1, right? And then I want to say that it must oh, okay. Yeah, it must wait. You have a disk of radius 1. Oh. Why? Okay. Okay. Let's see. Sorry. Yeah, we know that the imaginary part of Z is so sorry, I shouldn't do that stuff. Okay, sorry. All right, so imaginary part of Z is within 0 over 2 of one of the numbers. Okay. And then the real, okay, so okay, okay, and the real part of Z is within one half of these numbers, right? So what happened? So yeah, okay. So we have the picture that I stayed there, and then what happened? Why we cannot contain a disk of radius 1? Oh, okay. So if it does, yeah. If it does, yeah. So if it does, then the center of yeah. So yeah. Yeah. Wait. Oh. Okay. Never mind. I was just sorry. I was just yeah. Wondering. Okay. All right. So never mind. So let's continue. So Alright, so uh, what happened? So okay, and hence the image of D okay, this is D, okay. Wait, what is D? Wait. Wait. I think this D is, wait. Okay, so, I think this D is this D, okay. Let's see, okay. Under FE cannot contain a disk of radius 1/1 minus theta r sine prime okay, let's see why it holds. So yeah, sorry, yeah, so wait, never mind. So the image of D on the FZ cannot contain a disk of radius, yeah, why? Oh. Okay, I still got some time. So, all right. Okay then. Okay, so image of D under FZ cannot contain a disk of radius 1/1 minus theta r phi prime theta, right? So what's it called? Wait, what? Oh. Wait. Oh, okay. Okay. So, okay. Okay, so I hope, okay. I'll I'll leave it to you to figure it out. Okay, I'll leave it to you to figure it out. Okay. Oh, wait, yeah, maybe I'll do it. So, okay, no, okay, okay. So the thing is that here, this image D under this FD. Okay, so let's see y is something like this of radius that. So, okay. So the thing is, oh my. So the thing is, if you time now. Oh, okay. So, all right. Maybe I think I can